Hey guys, so we are back. Today we're going to be doing section 4.3 over graphing functions. And now, when we say graphing functions, I don't mean we're going to take 30 different points, calculate their outputs, and then draw a best fit line. No, we're going to use the machinery we have developed with analyzing the derivative and apply that machinery to graphing functions. See, just plotting a bunch of points doesn't tell you anything about the structure of your curve. It tells you where it is at certain points, but it doesn't tell you which direction it's facing. How sharp is its slope? How flat is it? What kind of concavity does it have? Is it a bump or is it kind of more of a straight line? You don't know that by just plotting points. But by using this machinery we have developed with derivatives, we can actually dive in and analyze these functions at a deeper level so we can get a clearer picture of their behavior. Now, I'd like to throw this disclaimer out at the very beginning. These functions are relatively Mickey Mouse. They're polynomials, trig functions, basic things we already know what look like. So you might be asking yourself, why are we spending our time doing this? Well, that's because we need to practice with the machinery first. We need to practice on these simple examples and make sure we are comfortable with how these tools work. Because once we are comfortable with how these tools work and we're confident in our abilities with it, then we can go off and tackle much harder problems. Because when you're attacking a hard problem with new machinery, when something goes awry, you don't know if it's your understanding of the problem or your understanding of the tools. So we're going to remove that question. We are going to hammer home our knowledge of the machinery itself. All right, so with that, let's get started. So recall these facts. If the derivative of f with respect to x is greater than 0, that means f is increasing at that point. So calculate the derivative, plug in a point. If it's positive, then f is increasing. If you kind of have a little trouble with that, think about what it means in terms of tangent lines. If the derivative at a point is positive, that means the slope at the tangent line is positive, or it's increasing. So it's kind of going in this direction. It's going upwards. So the function is increasing, so to speak. And when we're talking about this, we're talking about going from left to right. So if the derivative is positive, f is increasing because the slope of the tangent line is positive. So the function is going the upward direction. Now, the exact same thing. If the derivative of a function at a point is negative, that means f is decreasing. So once again, think about the tangent line. If the derivative at a point is negative, that means the slope of that tangent line is negative. So it looks like this. And then that tells us that this function is moving in the downward direction. So the function is decreasing. And now we're going to move on to the extreme value theorem. This is what we covered in the last section. So if you did not watch those videos over section 4.1, please make sure you go and do that now. So to find the relative maximum and minimums, the extreme value theorem tells us we only need to check the critical points, also known as relative extrema, and the boundary points. So to recap the extreme value theorem, if we have a continuous function f on a closed interval a to b, then we know that there exists an absolute maximum and an absolute minimum. But the thing is, these maximum and minimums can only occur at critical points and at the endpoints. Now, what do I mean by critical point? What is a critical point? Well, as we went over in section 4.1, critical points are just the points on a function that force the derivative to equal to 0 or force the derivative to not exist. So graphically, we're looking for the points that make the tangent line flat or horizontal, or make it so that there is no tangent line at all. So these are important things we need to remember because we're going to be using this for the remainder of this lecture. All right. So that's enough of the recap of some of the machinery we have. Now we're going to move on to one of the more important things in this chapter, the first derivative test. Now, I know that's a lot of text on the screen, but just bear with me. We're going to go through this step by step. So let's look at step 1 right here. Forget about step 2. Forget about that. We're just going to focus right here on step 1. So for this first derivative test, the first step is to find all of the critical numbers of a continuous function f defined on an open interval a comma b. So, to put that simply, find all of the critical points. Take the derivative, figure out where it's equal to 0, and figure out where it doesn't exist, because that will give us all of our critical points. Now the next step, we need to classify these critical points. So this is a first derivative test. That means we're going to use the first derivative to test something. What are we testing? The critical points. Why? To determine if they are the relative extrema we have been looking for. So here's how we're going to classify critical points. We say f of c is a relative maximum if the derivative of that point is greater than 0 for all x values near c and less than c, and f prime of x is less than 0 for all values near c and greater than c. Now, that's kind of strange. So let's just put a little graph right here just so we can kind of visualize this thing. So let's suppose we've got a Cartesian plane, and then we got some graph that looks like this. Well then, right here, we have a relative maximum. Just by eyeballing that, we can tell, because just looking at that, we see the little bump right there. We notice that we have a horizontal tangent line right here. The function bottoms out. So this point right here, I'm just going to kind of highlight that a little more, is a relative maximum. We have a horizontal tangent line. We know it's a critical point. And eyeballing that, we can tell. But the first derivative test is giving us a way to do this analytically. But how is that? So let's look at this first condition, that the derivative is positive for all x values near c. In other words, the function is increasing for all values near c, but less than c. So these values right here, notice how this function is increasing. As we get to that point, it's going up, it's going up, it's going up, it's going up, and then it stops. And then the second condition comes in. The function is decreasing, or it's going down for all x values near c and greater than c. So what these conditions are saying is, it is a relative max if at that point it has a horizontal tangent line, or the tangent line doesn't exist, so it's a critical point, and if all the values a little to the left of it are beneath it, and all the values to the right of it are beneath it. That's what this is saying. Now, for it to be on the left side, we need the derivative to be increasing, because it's going up to that point. And then we need, to the right of it, we need to be going down. Imagine climbing a hill, and we have the top of it, it's the highest point. When you're walking up to it, your elevation is increasing. You are going upwards right up until you hit that point. And then once you hit that point, you're not going up, you're not going down. But then you go down the hill, you keep walking, and all of a sudden the slope is going downwards. You're walking down. So to be a maximum, you march up to it, you bottom out when you get there, and then you go in the decreasing direction, just like this. You go up just to the left of it, and go down just to the right of it. Because remember, positive derivative just means the function is increasing. Negative derivative means the function is decreasing at that point. Now, we can build the exact same theory for the relative minimum. Just by eyeballing this function right here, we can tell that right here, there is a relative minimum. It kind of flattens out right there, kind of like an inverse plateau. So the first derivative test is telling us that if we take this point that has a horizontal tangent line, but if it's a tangent line, it really should, be tangent to it. So we have a horizontal tangent line here, i.e., this is a critical point, and if the derivative is negative for all the values right here, so the function is coming down to that point, it is decreasing down to our critical point. It bottoms out when we get to our critical point, and then after that, it starts increasing again. That means we have a relative minimum. So think about what it means to be at the bottom of like a canyon. You walk down to the point, you're going down, you're decreasing, you're decreasing, you're decreasing. You hit the bottom, and you're no longer decreasing because you're at the bottom. And then the only way to go is up. So you have to keep going up. Really, all of this test is looking at this, and is the point we're looking at the top of a bump, or is it the bottom of a bump, or is it neither? Because it can be neither. You can have something that looks like this. So let's draw this. This is actually a pretty famous example. In this case, it's actually the function x cubed. So let's go ahead and sketch that. So this is f of x equal to x cubed. It actually has a critical point at the origin, right here. It actually has a horizontal tangent line right here that you can't see because, well, that's the axis. But there's a horizontal tangent line at the origin right there. But notice, the function is increasing to that point. It's increasing, it's increasing, it's increasing. Then it stops. It's no longer increasing. It's bottomed out. It's leveled out. But then, as we continue going to the right, the function is still increasing. This is not a relative maximum. So if you just said every critical point is either a relative maximum or relative minimum, this example contradicts it. This is a problem. So this is why we have to check to the left and to the right. Think limits. So to know the limit exists, you have to look at it from the left, and you have to look at it from the right. To know if this is a relative maximum or minimum, you have to look at it from the left or from the right. So to be a relative maximum or relative minimum, it has to be a critical point. But just because it's a critical point does not mean that it has to be a relative maximum or a relative minimum. All right? So what we're going to do is we are going to use the first derivative test to find the relative extrema of functions. Where does it top out and where does it bottom out? Where does it change direction? So that's the first step in going towards graphing these functions. Okay, so let's actually look at some examples here. Consider the function f of x is equal to x cubed minus 3x squared minus 9x plus 1. First step, where is f increasing and where is it decreasing? So the strategy we're going to use here is pretty basic. It's the thing we're going to use every time. We're going to figure out where the critical points are, and we're going to use that to determine where is this function increasing and decreasing. Think back to section 3.4 with the rectilinear motion when we were looking at a particle's movement going left or to the right. To figure out where it's increasing or decreasing, the easiest thing to do is to figure out where is it not increasing and where is it not decreasing, i.e. where is it stopped moving. It's the easiest thing to do. There is going to be more places where it has stopped moving than where it's positive or where it's negative. So we're going to rule out those possibilities. It's the exact same strategy we did in that section. So the first thing we need to do is calculate f prime of x. Well, f prime of x is just 3x squared minus 6x minus 9. Pretty straightforward. But now we need to solve this when it's equal to 0, because the function f is increasing where the derivative is positive. It's decreasing where the function is negative. So we're going to figure out where it's doing neither, i.e. where's the derivative equal to 0. So set 3x squared minus 6x minus 9 equal to 0. But notice there's a 3 common in all three of these terms. So I'm just going to divide through by 3. And so we get x squared minus 2x minus 3 is equal to 0. Excellent. Now, I don't know about you guys, but I see something like this. All I want to do is factor it. So that's what we're going to do. So we get this is equal to x minus 3 times x plus 1 is equal to 0. That's the standard technique for solving these. Now, if you don't recognize this factorization, there's another strategy you can use. You can use the quadratic formula. This is a quadratic function, so you can use the quadratic formula. The quadratic formula will give you the roots every time, every day of the week. Even if the roots are imaginary, it's going to give you the roots. Quadratic formula, you cannot go wrong. But personally, I find it, if you see the factorization, use the factorization. Much easier. So we have this factorization of this quadratic. We know it's equal to 0. So these are two numbers. X minus 3 is a number, and x plus 1 is a number. Since their product is equal to 0, one of these two numbers must be equal to 0. So all we have to do is figure out what two numbers make these equal to 0. Well, the first obvious one is x is equal to 3. When you take x equal to 3, you plug it in here, you get 3 minus 3 is 0. So this product is 0. So this is a point where the derivative is equal to 0. And also the point -1. Plug -1 in here, this product will be 0. And thus we have our 2 points that we are looking for. Now, these are the 2 points we're looking for. This is where the derivative is equal to 0. Now we have to determine where is the function actually increasing and where is it decreasing. So just like in this 3.4 section, we need to build ourselves a little table here. So that's what we're going to do. We're going to break this up into 3 partitions. So just like we would on a number line. Except right here, we're going to call this x is equal to -1. And this is x equal to 3. That's a horrible 3. 9. So we know the derivative is equal to 0 at these points. We know that. We just calculated that. But see, these are the only places the derivative is equal to 0. That means everywhere else, the derivative must be positive or it must be negative. It must be. And since this function is continuous, all we have to do is pull out those representative points. Here, I'm going to pull out x is equal to -2. Here, I'm going to pull out 0. And here, I'm going to pull out 4. Because these points represent these entire intervals. Because suppose right here that the sign of f prime of 0 is negative. Suppose f prime of 0 is negative. That means at this point, the derivative is negative. And since the derivative is negative at this point, it must be negative for every single point on this interval. Because if it's not negative, then it must be positive. But the thing is, this function is continuous. And so by the intermediate value theorem, it cannot go from negative to positive without becoming 0 first. So that's why we found these values first. We figured out where it's equal to 0. So if we pull out a representative from this interval, whatever the sign of the derivative is at this point, that's the sign of the derivative on the entire interval. It is just like that section 3.4 in rectilinear motion. So here's what we're going to do. First things first, we're going to figure out what the sign is on this first interval. So let's calculate f prime of -2. Well, that's just equal to -2 minus 3. -2 plus 1. Well, that's just equal to -5 times -1. But that's greater than 0. A negative number times a negative number is a positive. So that tells us on this interval, the function is increasing. So I'm just going to draw an arrow right there to remind myself this function is increasing at this point. Okay? So the function is increasing at this point. Now let's check 0. Let's calculate f prime as 0. Well, that's just going to be equal to -3 times 1. But that's just going to be less than 0, right? Negative number times a positive number is negative. So that means at this point, or at this interval, the function is decreasing. Noticing a pattern here? And now we're going to calculate f prime of 4. F prime of 4 is equal to 4 minus 3 times 4 plus 1. Well, that's equal to 1 times 5. But that's a positive number times a positive number. So that's greater than 0. And so that means during this whole interval on the right, this function is increasing. So now we have labeled all the intervals where it's increasing or decreasing. So let's just write that neatly over here. So where is it increasing? Well, it's increasing on this interval and this interval. And now we need to write these in interval notation. So it's increasing on -infinity up to, but not including -1. Why is it not including -1? because we calculated the derivative at that point and it's equal to 0, so it's not positive. And we're going to union this with this interval over here on the right. Now, what is that interval on the right? Well, that's 3, infinity. So that is where this function is increasing on this interval right here. Now, where is it decreasing? Well, we're going to do the exact same technique. Look at the intervals where the function is going down. And it's only going down on this middle interval right here. And what is that middle interval? Well, it's the open interval, -1, 3. So this right here is where the function is increasing and decreasing. How do we do this? We calculate the derivative. We set it equal to 0. We found the roots of the derivative. We built our number line over here, plotted our zeros or our roots, and then from there we pulled out representatives from all of the intervals, calculated the derivative at those points, and remember, calculated the derivative, not the function, the derivative at those points. And then we determined the sign of those values, because we don't care what the value is. We just care if it's positive or if it's negative. And using that, we can actually paint a picture of the intervals as a whole. And then for our answer, we just extracted this information on this table using interval notation. So that's it for that part. Now let's go on to the next question. It says, find any relative extrema. Now, from that first part, we actually did a whole lot of the legwork already. So I'm just going to go ahead and copy down that little chart we just had. So we had our number line, we had our 3 intervals, and here x is equal to -1, here x is equal to 3. On this left interval, the function was increasing, on this function interval is decreasing, and on this one it's increasing again. So, recall, what does it mean to be relative extrema? Well, that means it has to be a critical point, and then we have to classify it as a relative maximum, a relative minimum, or neither. Just because it's a critical point does not mean it's relative extrema. But if it's relative extrema, then it must be a critical point. Now, this is where we're going to use the first derivative test. And the first derivative said that a function is a relative maximum if it's a critical point, and if you look just to the left of it, the derivative's positive, and you look just to the right of it, the derivative's negative. Do we have one of those here? Yes, we do. Right here, at x is equal to -1. We know x is equal to -1 is a critical point, and if we look to the left of it, the function is increasing up to that point, so it's rising up to it. It flattens out when it gets there, and then shortly after, it starts decreasing again. So that's why I did this the way I did. I didn't just use pluses and minuses. I actually kind of drew these arrows because it visualizes this. Visualizes going up, stopping, and coming back down. So that tells us x is equal to -1 is a relative maximum, or is where a relative maximum occurs. So relative maximum occurs at x equal -1. But what is the relative maximum? Remember, where a relative maximum occurs and what it is are two different things. X is equal to -1 is just telling us where it is. But how to calculate what the relative max is, all we have to do is plug it into the function. That is just f of -1. Well, that's just equal to 6. Now notice here, I didn't plug it into the derivative. I plugged it back into the function. So it occurs at -1. The relative max is equal to 6. So we can say that this is equal to -1, 6. It is very useful to write this as a point when we're told to find the relative extrema. If you're told to find what is a relative maximum, that's 6. If you're told to find what is the relative minimum, you just write whatever the relative minimum is. If you're asked where it is, you write x is equal to -1. But if you're just told to find the point, then this is what you're looking for right here. This point, -1 comma 6. Because this tells you where it is, and this tells you what the relative maximum is equal to. So when you're asked to find the relative maximums, write them as points, where it occurs, and what the value is. Now let's do the same thing for the minimum. Well, let's look at our only other critical point right here, at x is equal to 3. We notice just to the left of it, the function is decreasing. We're going down to it, and then it bottoms out right here, and then it starts increasing again. It goes in the upward direction. So from the first derivative test, that tells us x is equal to 3 is a relative minimum. So we have a relative minimum at x is equal to 3, and the relative minimum is equal to f of 3, which is equal to -26. So we have a relative minimum at 3 comma -26. And once again, write this as a point, as a tuple. It tells you where it is, and it tells you what the value is. So this right here, it's -26. That is the relative minimum. 3 is where it occurs. The same thing up here. 6 is the relative maximum. -1 is where it occurs. All right? So this is the process of finding the relative extrema. We use this table right here that we developed from the first part where we were determining increasing and decreasing, and we look where the function changes direction. If it goes up then down, well, that means you have a relative maximum. If it goes down then up, then you have a relative minimum. That's all you do. You build your table like this. Finding the relative extrema is as simply as eyeballing it and looking at what shape it makes. Relative maximums look like this. Relative minimums look like this. That's all there is to that problem. Now, I like to point out, your answers, as specified, need to be in this form, as a point, as a location and value. All right? But that's just finding relative maximums and minimums. Now we're going to introduce a new concept called concavity. All right, so let's look at concavity. So we say a function is concave up if the second derivative of f at that point is greater than 0. We say f is concave down if the second derivative at that point is negative. And we say x is an inflection point if f changes concavity at x and f of x exists. Now that we've defined those, let's look at what these different things are. So let's look at a function right here. Let's put a little Cartesian plane. Now let's graph just this again. Just something basic that looks like this. Yeah, I don't like that. Let's try that again one more time. Boop, right there. Excellent. So first, we want to talk about what does it mean to be concave up, or the second derivative is greater than 0. To be concave up, it needs to look like a U shape right here, like this. Right here. You know what? Let's do that a different color. Right here. This function is concave up. It is facing upwards. So if you hold a U shape to be concave up, the function looks like this. It opens upwards. So it looks like a smiley face kind of thing. It's just looking upwards. That's what it means to be concave up. Now, be concave down is the exact opposite. This is what it means to be concave down. The function is looking down. So if concavity is more like, what is it looking like? What direction is this function facing? So to be concave down, it's kind of facing downward like this. It's looking down. That's why the second derivative is negative. It is looking in the downward direction. And over here, the second derivative is positive. So it is kind of looking in the positive direction. Think like a slingshot you've pulled backwards. Which direction is it about to shoot that projectile? It's concave down, the second derivative is negative, and we're looking in the downward direction. Concave up, the second derivative is positive, and we're looking in the upward direction. Another way to remember that, concave down, concave, it looks like a little cave. So my optimization professor actually pointed that out to me relatively recently. I never thought about it that way, but it actually kind of stuck with me. So it's concave down if it forms a little cave. It's concave up if it doesn't form a cave. Now, as for inflection points, an inflection point is where it changes behavior. Right here. At this point, it goes from concave down to concave up, and the function exists at that point. So green, that is our inflection point. And then just to keep up with this, it's concave down if the function looks like in that negative direction. So, quick recap. Second derivative is positive, looks like this, facing the upward direction. We call that concave up. Second derivative is negative, it's facing downwards, looks like a little cave, and that's what we say is concave down. Where the concavity changes, that is what we call an inflection point. So where it goes from positive to negative. So an inflection point is simply relative extrema of the second derivative, where the concavity changes. All right. Now there's a professor at this university. His name is Dr. Brock Williams. He actually showed me a clever way of remembering this that it kills me to do this. It really does. But I cannot not show you because it actually is a pretty useful way to do it. This is the way to remember concave up. Smiley face. If the second derivative is positive, that means it looks like this. If the second derivative is positive, then that means that curve looks like this. Now, it's concave down, i.e. the second derivative is negative, it looks like this. So, negative, upset, downwards, frowny face. It's happy, it's positive, second derivative is positive, it's smiling, and it's looking like that. It's just one of those weird ways that you use to remember what concave up and concave down are. It's just one of those weird tools that we use. And now that we have these definitions, let's see if we can take this theory and apply it to our graphing situation. Consider that a function we've been talking about, f of x is equal to x cubed minus 3x squared minus 9x plus 1. We now want to determine where is f concave up and where is it concave down. Well, so what we have to do is find the second derivative, figure out where it's equal to 0, build our little table, and to figure out where does it change concavity, if it changes concavity. So, just to remind you, f prime of x in this scenario is 3x squared minus 6x minus 9. But now we need to calculate the second derivative. So f double prime of x, well, that's just equal to 6x minus 6. Now we want to figure out where it's neither concave up nor is it concave down. So we set 6x minus 6 equal to 0, or x minus 1 is equal to 0. Solve for that. That means x is equal to 1. Excellent. But now we want another little table like this. Get used to drawing these tables. Anytime you do a rectilinear motion, anytime you do a graphing problem like this, and when we get to it, an optimization question, you're going to have to draw a table like this. All right. So this point right here is x equal to 1. Now we need to test the concavity. So we need to pull out representatives from each interval. So here, I'm going to pull out x is equal to 0. Here, I'm going to pull out, what do you say? 2 seems like a good number. Remember, the representatives can be anything that's in the interval. It doesn't matter what number it is. You could choose negative 1500 if you'd like. Just go with the basic numbers, the simplest ones you can think of in each of these intervals. Makes the calculations easier. Now, that means, right here, where'd we go? There we go. F prime of 0 is equal to negative 6, which is definitely negative. So that tells us that at this point, this function is concave down. And since we already found the only place it's equal to 0, on the whole interval, it is concave down. And it looks something like this. Now that's for that interval. Now let's check f prime of 2. Well, that's just equal to 6. And that's actually greater than 0. So what that tells us, on this interval, it is concave up and it is facing in the upward direction, just like that. So now we have determined where this function is concave down and where it is concave up. So let's go ahead and write that down. It's always nice to have. So it is concave up. On which interval? Well, it looks like from 1 to infinity. And now we need to figure out where it's concave down. What's concave down on the interval negative infinity to 1 not included? It's because on this interval right here, negative infinity to 1, oops, wrong thing. Let's do this. From negative infinity to 1, the second derivative is negative, so it is decreasing. It is facing downwards. So that's why it's concave down here. From 1 to infinity, second derivative is positive, so it is concave up on this interval. So that is how you determine where it's concave up and where it's concave down. All right. Now we want to use this information to find any inflection points. And real quick, let's go ahead and draw that table we just had. So this is x is equal to 1. And we know it is concave down here, concave up here. So recall, what does it mean to be an inflection point? An inflection point is where a function changes concavity and where the function exists. So the function exists at x is equal to 1. This is a polynomial. Of course it exists at x is equal to 1. And now we need to determine, does it change in inflection at this point? So here it's going down. Here it's going up. I would say that changes concavity. So that means the point 1 comma f of 1, which is just equal to 1 comma negative 10, is an inflection point. Notice it asks for a point, so you need to give it a point. Extrema, relative extrema are points. Where it is, what's its value. Inflection points are points. Where it is, what's its value. It's at x is equal to 1, and it's equal to negative 10. Writing it as a point gives you a whole lot of information in a compact manner. Now, for like the current call, why have we been doing all of this? What does this give us? Well, now we can use all the information that we have developed to do one thing. We can use this information to graph it. Now, I've already gone ahead and copied down all of the information that we have gathered from this problem. We know where this function is increasing. We know where it's decreasing. We know the relative maximum. We know the relative minimums, the inflection points, and the concavity on the different intervals. Okay? So now we're going to use all this information to graph it. First, let's put some axes down. Well, notice in the negative direction, it gets pretty big pretty quickly, but we don't really go left or right too much. So we're going to call this as 1, 2, 3, -1, -2, etc. And then how do we want to do in the negative direction? Well, I'm going to say let's do this in factors of, let's say 10. So let's call this point right here -10, -20, etc. 10, 20. Now let's plot this function. Sounds like a bad game show. So let's go ahead and graph this. Let's go ahead and put down all the points we know where are. So we have 3 listed, let's go ahead and plot those down. So we know we have a relative maximum at -1,6, so about right here. That's a relative maximum, so that's going to be the top of some kind of bump. Now, relative minimum, that's going to be at 3, -26. So that's going to be about right here. So we now have a maximum and a minimum. Let's go ahead and plot that inflection point. Right here, that's where it's going to change concavity. Now we are going to use this information to graph this function. Now, to do this a little more accurately, you're going to want a few more points in here. You're going to want a few more points. It was going to make it more accurate. But here's the thing. I'm looking at your understanding of the first derivative test, understanding what it means to be increasing, decreasing, relative extreme, and concavity. As long as your graph portrays this information that we have written down here, as long as you get all this information on there, I'm good to go. I really don't care how good of an artist you are. That's not why we're here. So, this is about as good as a drawing as I expect. We know that it's increasing from -infinity to -1. And we know on that interval, it's concave down. It is facing downward. So we know it's going to look something like this. It's facing concave down at a relative maximum. It is still concave down, but now the function is going to decrease. So it's going to go down in this direction. But right here, I'm going to fix that. So it's going to go in the downward direction. But notice it's still concave down the whole way through. There is no changing of concavity. But when we get to this point, 1, -10, that's an inflection point. That's when we're going to go from concave down to concave up. So that means we're still heading in the negative direction. This function is still decreasing on this interval, but now it's concave up. So it changes the concavity until we get to right here, a relative minimum. That's where it bottoms out. And then we go back to increasing from 3 to infinity. This is as good as a graph as I expect. It portrays all the information here. It shows that we're increasing from -infinity to -1 and from 3 to infinity. It shows that we're decreasing from -1 to 3. It shows that it is concave down from -infinity all the way up to 1. And it shows that it's concave up from 1 to infinity. And shows an inflection point right here. This is the best kind of graph I'm expecting. It really is. Just show me that you understand what this information is telling you. Just show me that you understand what it's telling to you. And if you can do that, then we are going to be in good shape. Now, because this video is long enough, this is where I'm going to cut off part 1 of this video. Part 2, we're going to go over more examples and the second derivative test. In this one, we had the first derivative test, so it makes sense that we have a second derivative test. Okay, I will see you in part 2, where we will have more fun with math.